Great. Sorry. Evan, do you want to start it off?
Oh, okay, well, so you the thing you have to do in this case, it's a national service and they can, you know, it's like that service. It's like, it's so that's all. It will actually give you. So better still for that laptop. Which is something you can see rather than rather yeah, the same. Somebody else, I did it months there. You're just around my house, it's a 20-30 mile range. Other places. But you don't know. I'm very rotten. Oh, yeah, yeah. I forget, yeah, so I know where you're talking, I forget its name. Yeah, that.
Have to get going.
You have any lurkers outside?
Good afternoon, everyone. Thank you for coming. Today is University of Scranton jointly hosted IEEE seminar and the W3USR and HAMSI seminar. I'm going to hand this over to Evan Remison.
Morning, everyone. Thanks for being here. Just to introduce myself, my name is Evan Armission. I'm a senior electrical engineering major with a minor in operations management, and I'm the president for our student chapter of IEEE. So every week we have a seminar like this one. It looks a little bit different where we bring in people to speak. And so this week is just a little bit different because we're doing it with our radio club as well. But we just kind of want to break down the attendance here. So if all these students that are a member of IEEE could just stand up for a second, kind of represent our attendance from the club. Just all students in general. Great, thank you very much for being here.
Thank you very much, Evan. So thank you, students, for coming. And we also have some special visitors from out of states, and yes, multiple states. So first, I'd like to welcome the members of the Fairlawn Amateur Radio Club from New Jersey. Yay! What exit? Somewhere around what, 155 or something, 160? Yeah, great. Okay, and then we also have the Binghamton Amateur Radio Club. Yay! In the Binghamton Amateur Radio Club, they also have this Copernic Observatory, which is a public observatory in Binghamton, New York, about an hour and a half away from here. So if you haven't been there yet, you should go on, take a look at that, come on up and see that. Before I introduce our guest, I just would like to recognize a couple other people who might be able to say a word of welcome. First, we have Dr. Andrew Berger, our department chair and IEEE moderator. Would you like to say a word of welcome?
Welcome, being here and enjoying. We ordered specially the weather for you. We haven't had, since Nathaniel joined us, we started having big enough events that we don't normally fit in normal room anymore. So this is the fourth event that we are here on 133. So welcome again.
Thank you so much, Andrew. And also, Dr. Carolyn Berry, the Dean of the College of Arts and Sciences.
Hi, it's a pleasure to be here. It's great to have all the folks that are working with Nathaniel as far as the Amateur Radio Club. I've heard lots about it and toured the facility and know of all this great work. And so I'm eager to hear more and learn more about it. I'm a developmental psychologist, so I have a lot to learn. So great to be here.
Thank you so much, Carolyn. And let's see, is Elmer? Yes, and so now I'm going to introduce our two guests. We have first Elmer Mustard. Please stand up. So we have Elmer Mustard at 3AGE and our speaker, Robinett AI6VN. And they have been with us on this week. They've been here since Monday night, not only preparing for this presentation, but they've also been very busy at my house installing personal space weather station equipment, working with we have experimental antennas up there, experimental receivers. We've had a number of students working on senior capstone projects and helping with that work. So if you're a student who's participated in the field work this week, please stand up. Okay, wonderful. So thank you very much. All right, and now it's my pleasure to introduce Robinett AI6VN, who has come all the way from San Francisco to be with us today. And I've known Rob now for, what, maybe 8 years or so? 7 years?
Yeah, at least maybe 9, maybe 2016.
Yeah, maybe not.
Before the 2017 eclipse.
Before the 2017 eclipse. And Rob is one of the people that has not only been a HamSci collaborator, but he has really transformed the way we collect data and operate in HamSci. So I'm very excited to have him join us. And he started and founded his own group called the WSPRDaemon group, which he will tell you about. Now, when Rob asked me what type of presentation he should give today, I said, he's like, who's my audience? I'm like, well, it's a rather diverse audience. We have fairly young college students who are engineering students and engineering management students and physics students. And we also have amateur radio operators from the community. So we want to be able to speak to all of those people. And one of the neat things about the HamSci community is that we often get to work with people who have really had fantastic careers in addition to their work with HamSci. And so Rob has a lot of experience leading startup companies in Silicon Valley, high-tech startup companies. And so I asked him, I said that hearing more about that might be of interest to the younger engineering students here. So the first part of the presentation, he's going to talk about his earlier life. In the second part of the presentation, he's going to talk about what he's doing to advance the WSPRDaemon project and collaborate with HamSci. And throughout all of this, this is going to be a little bit more, there's going to be some question and answer. So if you have any questions, feel free to ask. And Owen here will have this microphone and he'll be able to run around and let you speak. So, Rob,
Can you hear me?
Go ahead.
Am I on?
Yay.
Okay, well, thank you all. Thank you, Professor Fazell, for inviting me, not just this week, but to the last 6, 7 years of my life, as I become more and more engaged in the scientific investigations. So while the title of this is about the system we've developed, I'll give you a little background of me, how I ended up here speaking to you today. I am, let's see, how do I get to the next page? Wake up. It doesn't want to. It's trying to be intelligent. I don't want any intelligence more than, how did I?
I'll work on this so you can keep talking.
Okay, let's get back to my background is I'm actually a graduate of Loyola High School in Los Angeles. So I have Jesuit training. Thank you. So, Jesuit training. And in high school, I was the president of the Amateur Radio Club. So after Loyola, I went to Stanford University during an era when engineering was out of favor, Vietnam War era, and I had other interests. So I actually graduated with a BA in history and really didn't take any engineering courses. But almost immediately, my fascination with engineering brought me back into engineering professional life. And I went back to Los Angeles and worked in the professional audio industry. Very soon became the chief engineer of Westlake Audio, which was the premier vendor and builder of recording studios in Los Angeles and worldwide. So we had equipment, and we actually had construction crews that went out. We would build people would give us a shell, and we'd go build a whole recording studio for people, like Michael Jackson, Queen, Donna Summer, ELO. Those kind of people. So that was an exciting time in the music industry, but that business is not fundamentally technical, and people really just wanted, if it were a little bit louder, it always sounded better. And that kind of discouraged me. I didn't feel like it was a long-term environment that I wanted to work in. But one of my final projects was to build the studio that Michael Jackson recorded the Thriller album in. And I actually never worked with the artists. I knew Quincy Jones and Bruce Swedien, his engineers. But my hearing, you'll probably experience it, has degraded in the last few years, more than many people of my age. And my conceit is that I sacrificed my hearing to Michael Jackson's Thriller album. One person who did introduce me into my next stage of my career was the chief engineer of the group Steely Dan, and they were recording an album, now famous album called Asia. And he came to me and said, the guys want to use a computer to record a drum track and be able to play it back on the computer so it's exactly the same every time. Do you know anything about building such a thing? And I said, I know nothing about computers. And he said, if it's interesting to you, you could go and take a course out at so I took a course, became interested in computers, started applying them to audio problems, but rapidly became much more interested in computer systems. So I moved back up into Silicon Valley and got kind of a master's in I would say in computer science by working at a company called Metaphor Computer Systems, which was a spin-off of Xerox PARC. Many of the key people at Xerox PARC were there. So in 2 years, I've learned everything I've really ever known fundamentally about computer engineering from being mentored by the people there. From that, I migrated into professional video broadcast equipment, building real-time MPEG encoders and transcoders. And eventually, after being in a couple of those, I went and formed my own. A first company called Skystream Networks. These were the kind of classic venture-funded startups. We go up and down to the VC funds on Sand Hill Road in Menlo Park, kind of the Park Avenue of high-tech finance, and make a presentation. And I was able to raise money first for Skystream Networks in 2096, and to do a video processing company. That was eventually sold to Ericsson years later. But then I went on to found a second company, Modulus Video, again funded by institutional ventures groups. And that was very successfully sold to Motorola. And I was an engineering fellow at Motorola for a few years until I was able to escape. And when I escaped it, I had never been involved in radio the whole time. I mean, I was in television, but it was really IPTV and so on. But I did become interested. I actually really became interested when I broke my leg so severely that I was laid up for 6 months. And my oldest friend came in and said, there's all this new technology in ham radio. It's really different than when we were doing it. This is my friend from the high school days. And you ought to explore it again. So I learned very rapidly, I learned about the whisper system, digital transmission, and became involved in that. And for those of you, I don't know how familiar you guys are with, many people use, of course, FT4 and FT8 for communications these days on the shortwave band. But they're included in the software package, the WSJT package, is a beaconing mode called Whisper, Weak Signal Propagation Recording. The Whisper mode is available on every transceiver can do it, but it's not interactive. It's beaconing, and one would think that this is relatively uninteresting compared to having QSOs with people across the world. But as it turns out, for me at least, and for the circle of people I work with, I've gathered over time, it's become a tremendously fascinating way to learn about the ionosphere, radio propagation, radio reception hardware and software. And to that end, I recognized that there seemed to be a gap in the capabilities of the software and hardware systems that were being used for Whisper. That being that you really had to take a typical case is somebody takes their transceiver and plugs it into a computer and tunes to one band, and you've got this $2,000 transceiver talking to your $1,000 PC, and you really can do nothing else with it. You could sit there and look at it, while it transmits or receives whisper signals. So I saw the opportunity that this was a really inefficient way, one band at a time, to utilize Whisper, and that my skills, my programming skills, system software skills, might be utilized to develop a software and hardware system to better utilize and exploit the signals that were being created by the Whisper world. There are about, at any one time, almost 4,000 beacons transmitting Whisper around the world. So, and there's anywhere from 1,500 to 2,000 receive sites listening for Whisper beacon signals. So these are, in essence, computers talking to and radios talking to each other. There's no human direct involvement. So one would think this is like not at all interesting, in terms of personal interactions. But as it turns out, the community of people that run these transmitters and receivers are really my kind of people. And we get together online weekly, in fact, multiple times per week. We've developed hardware and software to record, and what are called spots. The reception reports are recorded on a global database where we can go look at them. Last year, 2 years ago, I kind of been on the side at on the ham side project, but seeing the difficulties that Hamsci was having developing the Grape 2 and receivers and the successor to it, I saw the opportunity to add the Grape recording monitoring capability to the Whisper system. So that has brought me into much greater communications with the Hamsci group, and it's been a wonderful experience in the last couple of years. So the system that I've developed consists of hardware and software. This is the receive system. Consists of a this is a state-of-the-art SDR, 16-bit to 129 megasample receiver connected by a USB cable to a Linux host computer. That's it. I mean, you can, until a couple of months ago, you could buy these for a total of $500 or so. And And this system is capable of listening to all of the whisper bands simultaneously. It can listen to all of the WWV and CHUs and record them for upload. So this system, an example of what comes out of these recordings is like other great systems, is you can see a spectrograph down at the bottom, which shows over time the frequency of WWV. In this case, we're looking at a 15 megahertz WWV signal over 24 hours. And so the vertical scale is in hertz. It's from -5 hertz to +5 hertz. And there's 24 hours of recordings there. So as you can see through the day, the carrier frequency at the receive site, and this is receptions at, this is a reception in Ohio, a site in Ohio. The carrier, WWV carrier changes its frequency, the receive frequency. And that change is the result of the motion of the ionosphere on the path between WWV and Fort Collins and Dayton, Ohio, in this case. So that Doppler shift allows us to interpret not only the motion, okay, the movement of the ionosphere, and of course but actually we can identify different paths. So there's actually multiple transmission paths from the WWV to the receive site. So this is an area that I think is almost entirely unrecognized by the amateur radio and only kind of lightly recognized even by the academic and research science community, that there are many more propagation paths. And as a result, there's things that are happening up above us in the ionosphere that I think we're able to learn from these recordings that are heretofore unrecognized or hardly understood. So this is exciting to me as because I get to be, after years of being an engineer and then an entrepreneur, I get to be at least associated with real science. And to me, this has been very gratifying for me. Both the scientific, intellectual, constant intellectual challenge. I've had to learn about new disciplines. Even in mathematics, there's a branch of mathematics called continuing fractions that we use to calculate frequencies and in the transmitters and receivers. So all kinds of continuous intellectual challenges, and the friendships that I've developed with and deepened with Elmer and Nathaniel and many others. So I hope that you would come away from this. What I hope one of the things you would learn is that you may find engineering very dry, and it sounds like you're working with with computers and so on, but that there's a tremendous social benefit and a community. You can join a community, not ours necessarily. Hopefully, we all find a community that matches our interest. And this happens to be the community that just matched my interest perfectly. I mean, I always wondered when I strung up in my backyard in Minnesota, strung up a long wire and built a crystal radio and had a cat whisker, and I could hear Baton Rouge, Louisiana. I always wondered, how did this happen? Where did these waves go? And it's now 70 years later that I'm actually starting to be able to learn what is actually happening. So if you as students, the students here, have some fascination with something engineering, it doesn't have to be radio, but pursue it. I hope you get the chance, like I've had, to pursue it and to return to it I'm not really retired. I actually have 2 little companies running, but this is by far what I spend most of my time at, is working on this stuff. So you can see here, these are the kind of ways we look at the data that we gather with this system. Here's the receives hardware. I've showed you most of it is right here. This is the Linux computer. This is a mini PC. It's really designed for gamers to use, but it has power of the current generations of CPUs are so incredibly powerful. And when married with the algorithmic advances that have been made over the years, there's a fantastic amount of computational power available in very inexpensive platforms. Similarly, the advances in software and have allowed us to simplify radios. I mean, you know, our history of radio was giant things with lots of coils and tubes and so on. It's where I started with. This device is really basically has two chips in it, a USB interface chip and a analog to digital converter. Well, three chips. There's an analog amplifier in front of it. So there's three. The essence is that it's a dead simple thing. It's called a direct conversion software defined radio. Unfortunately, this device, the RX888, this is only one that's available at the moment in the world. So that's one of our challenges. The third element that's made these Doppler shift investigations and the study of the ionosphere using Doppler shift measurements is the arrival of the GPS system. And the fact that we can now have in our own homes oscillators that are accurate and stable to microhertz. You know, they are incredibly for $170 you get a oscillator that has both time and frequency accuracy that allows you to make the kinds of measurements I showed you on the small Doppler shifts, a fraction of a hertz, are easily measured today. And there's and so that kind of capability has really is part of the transformation of our ability to investigate using simple home citizen science affordable equipment. So this is the received part of the chain. The Grape system uses WWV as its sole transmit site. Well, there's two of them. There's WWVH in Hawaii, which actually is kind of a problem because they transmit on the same frequencies. But what we've found is that we could very inexpensively develop I won't list all these things here. You can, well, hopefully we can make this available. This will come up on our website, and you can get the details about this stuff later, or you can contact me. But we realized about a year and a half ago, before the eclipse, maybe now 2 years ago, actually, time flies, that we had the opportunity that the eclipse did not really pass directly across WWV. But if we had a transmitter with equivalent stability, that a whisper transmitter, that we could locate these transmitters along the paths of totality and use that to get very clean measurements of the ionospheric disturbance that happened during the eclipse. So one of my new friends, really collaborators, Paul Elliott, WB6CXE, took that idea, and 3 months later he had this device available. And this is a dedicated whisper transmitter. So it's a companion to the receiver. The receiver can receive all the bands simultaneously, but most whisper transmit sites transmit on only one band at a time. So that was a problem during the eclipse, because the eclipse was only going to last, totality was only going to last at most about 4 minutes. So the whisper transmissions, right, each transmission is 2 minutes long. So most whisper transmitters transmits for 2 minutes on one band, and they shift to another frequency and transmit for 2 minutes. So that meant that they were only going to be transmitting at best on 2 bands during the path of the totality. So Paul's whisper sound transmits on all the bands all the time. And with the combiner that's up above there, it's a filter box, we could connect it to a single antenna, a multi-band antenna, and be transmitting on all bands all the time through the duration of the eclipse. So this very much mimics the studies you can make with WWV, which transmits on 2.5, 5, 10, 15, 20, and 25 megahertz. Well, the whisper songs can transmit on, the 80 meter, the 3.5 megahertz, 7 megahertz, 10 megahertz, 14, all these bands simultaneously. Not knowing, we don't know what's going to happen during the eclipse. So having signals being sent on all the different frequencies meant that we had the opportunity to see a better opportunity to see what the effects were, whatever the frequencies were. And it did surprise us, okay? We thought that the biggest effects, the most interesting effects would be at the higher bands, where there's the biggest change in the ionospheric density during the shadow of the eclipse. As it turned out, the greatest area of interest and the data that gave us the most were the lower frequencies, the 3.5, 7, and 10 megahertz bands. From those, from the observations we got during that 4-minute window, okay, there's 2 sets of transmissions on all the bands during that window, gave us some ability to understand the motion and the depth of the ionosphere during the eclipse in ways that we could not have ever hoped to do elsewhere. And a paper was produced by my close collaborator and friend Gwyn Griffins, G3ZIL, who's in England. Gwyn did a careful study, deep study of the measurements we made with this system, and identified some characteristics of the ionospheric motion during the eclipse that I think no one else had identified. We certainly were also able to compare it against other ways to measure the ionosphere, like ionosonde measurements during it. And he found that our measurements correlated well with the ionosphere. In fact, in some sense, we had higher resolution than the ionospheric ionosonde measurements. So we now have the 2 components, the receive system, inexpensive receive system, the inexpensive transmit system. And these are the components of what we're going to present and be deploying as part of this Ham-Sly DAISY2 deployment in the next year or 2. So that's this is the core of what I've been developing. I didn't develop the whisper sound. I did conceive of it. I want to take a little bit of credit, but Paul really implemented it. So I was going to show you. Let's see if I can find it. Yeah. So for those of you, you're seeing that? Yeah. This is one of the ways we look at the data we gather. So all of the receive sites around the world upload their data to a database called WSPRnet.org, and we can do queries using it's a publicly available database. And this is one interface. Another one of our collaborators created this web page where you can go and look and say, okay, in this case, I'm just looking at the last 24 hours, okay, to now. And this gives me a list of all the transmitters, the receivers, and how many reception reports they received. So John, John Melchor, he's a German, has a vacation home in the Canary Islands. The Canary Islands is the best QTH in the world. because you're one skip hop from Europe and one or two from most of the US. So he's always going to be, given that he has have really good sight. He's running WSPRDaemon on, on RX888s and others. So he's always going to be the best. So, but you can click here and say he reported in 24 hours, 74,000 spots. Those are signals that he received over the 78,000 of them. Okay. And there were, if you sort, I'm going to click and sort on unique, there were almost 3,000 different transmitters that he identified over the last 24 hours. So as I said, there's something like 3,000 to 4,000 transmitters. There aren't that many receivers. So he has another site. He has also in the Canary Islands. It does almost as well, but it doesn't have it. This is the third one on this list. I could go down, but most of these people are running WSPRDaemon software. There's about 8 million to 9 million spots uploaded each day, each of which is a potentially useful item for ionospheric research. So so this is a resource for radio science that Nathaniel identified years ago. And I think we've barely scratched the surface of what we can learn about this from this. So if we, this is what we did is when we set up these antennas out, this is a SQL database. So I did a query. This is a whole nother area of computing that I've been introduced to by this is databases. So that just did a query on an 8 million deep database, set of reports for and returned the results showing this is Nathaniel's site. There's actually, you're in there twice, Nathaniel, because of a mistake, a configuration mistake. But he has 3 antennas and 3 receivers, -1, -2, -3, out at his home that we installed and got up. Elmer put up the antennas. I configured the computers and the receivers. And so we can see that he has his -3 receiver, which is the SAS, okay, reported in the last 24 hours. It hasn't been actually running continuously during that period, but he reported over 20,000 reception reports. So in terms of the ability to understand what's going on, propagation, even if you're just a DXer and only interested in knowing what part of the world you could be potentially talking to, looking into these databases, these are real time. They're updated every 2 minutes. Okay, so you could go look and say, okay, let's go look and see what bands are open. So let's go to Nathaniel's, do a different part of the let's see, I need to go back. I'm going to do NAF, and this is the -3. Okay, so let's look for the last hour and see what he received. He received 620 spots in the last hour. So we can look at a map of it and say, okay, those are all of the receivers that transmitters that he heard here in the last 1 hour. And if I move this, you can see there, this is a transmitter that is actually a WSPR installed down in Antarctica at the German Polar Research Station, one of our, where there's also a WSPRDaemon grape receiver, also down there, located about 1.5 kilometers from the transmitter. It can't have the transmitters and receiver close together. So we're hearing him, and that's 13,000 kilometers away. These transmitters, these are 1 watt. We're looking at signals. Many of these signals are less than 1 watt transmit power. So it's not really, it seems to some extent, originally it seemed to me like magic, Okay, but the reality is we're looking at a very narrow signal. So unlike voice communications where you have to have 3 kilohertz or so of bandwidth, so you have 3 kilohertz of noise, we have 4 hertz of bandwidth. So we have only 4 hertz of noise to compare against our signal. So that by narrowing the bandwidth, we're able to greatly increase the sensitivity of the systems. So, yeah, so
With respect to that station down in Oregon, how do you know that that's necessarily the path versus, say, a long path? Is there?
yeah, at the moment, we don't know that, okay? And that's that is area we have to date worked very hard to increase the frequency resolution. So we now have we can measure the frequencies of these signals to, you know, to 10 millihertz actually is the resolution of the system. So we have very good frequency resolution. The next challenge is how do we get temporal resolution? Can we measure the time of flight of these signals? And we believe we can. But that requires that we have a very accurate to the microsecond idea of where our recordings start. Yeah, okay. And of course, transmits have to start at an exact time. Now, HAMSI has done work in this area using signals on the WWV carriers. And I think obtained very interesting results. But we hope to do better and be able to increase the resolution of the down into the order of tens of kilometers. And that I was showing you the spectrogram earlier. Let's see if I can get back to it. Yeah, back here. And if we go look at this spectrogram, let's see if will this play that? Yeah. If you look here, these look pretty messy in some ways. But if you look more closely, you can actually see up here. I can't show you, can't quite there. Maybe my cursor will show up on the screen. If you look up here, you see kind of ghost traces. Is that showing up? Yeah. You see that ghost trace? That's a WWV carrier, but it's coming from a different path. And there's more motion on that path. So Wen has done some studies in which he theorizes that these signals, the path that these signals are taking, one of the most obvious one is one that was only reported in the academic literature once, but that's a phenomenon called side scatter. Okay, normally we think that our shortwave transmissions are going to go directly from transmit site, following the great circle route to the receive site. That isn't actually the only path they can follow. That when that path, right, the MUF goes down and the ionosphere no longer carries it, there is a path to the side. Your transmit signal can go off to the side, reflect off of the ground or ocean, and come back. And the two reflective points where in the ionosphere are still ionized enough to propagate the signals. Those signals are typically 20 to 30 dB weaker. But the sensitivity of our systems now allow us to see those signals. Especially if you transmit with enough transmit power. I mean, this is a 10, 20 kilowatt transmit or something. It's so that there's the side scatter is still well above the noise. So there's other on other recordings. This mishmash of stuff you see is probably because of a combination of all kinds of different paths coming together. So it isn't, so increasing the temporal resolution might allow us to clarify these and separate these things out because we know about their time of flight. We could, here we only have one dimension, frequency and time. So anyway, that's a next generation of our systems. Did I cover? You have other questions? I was going to show you, there's I was going to show you one other thing before we go here. Is that I was showing you some ways to query this. Let's see if I go back here. This is one way to look at it. There's another one of our collaborators. Well, this is our home site, WSPRDaemon.org, where you can see eventually this presentation and so on. But we have other things. This is an example of another view. This is a live view of all the WSPR transmissions in the last 15 minutes around the world. So this is on 20 meters, 14 megahertz band. So you can see one of our problems is we've got a tremendous concentration of transmit and receive sites that are in North America and in Europe. You can see here's John down in the Canary Islands. So and we've got a few people in Australia, but such a scattering of small scattering. So we have the opportunity because this equipment is so inexpensive. There's the opportunity to establish transmits and receive sites around the world and monitor parts of the ionosphere that we can't look at. Right now, WWV allows us to look in North America and a little bit beyond. The problem, I think, looming problem is an avalanche of data. There's going to be avalanche of observations. We already have 8 billion spot reports over the last 15 years. We're going to generate 8 billion a month if we really were to deploy all this stuff. So sorting this and culling from this vast database and seeing what we could learn from it, I think is one of the great challenges, and that's a computer science problem. It's not really a radio problem. You need to understand the radio, but you really need to figure out how to do this. And we've also been exploring how to use AI techniques to investigate and identify different phenomena within the propagation from the database. But you kind of have to first understand, you've got to train an AI, and we're still learning about propagation from this data, new things from the propagation from this data. So I think that the AI is a challenge in the future. One more. Okay. Any other questions? I'll be around. I think we're going to lunch.
We still have a couple minutes for questions.
Okay.
So first, thank you, Rob.
Okay. That's on.
And I do want Owen to stand up, please. Owen has a microphone. So I would especially, if any students have any questions about either the ham radio or the whisper, or even starting companies in Silicon Valley.
Oh, we can't get anyone out. Oh, we got it. Okay, go Tigger.
Looking at this map, which is great, I'm noticing there's something coming out of Florida, and the arc going to Europe seems to be much higher than all the other data. Is there something specific to that arc, or is it just happens to be, I mean, back on you, if you go back toward the equator, you can sort of see this, looks like it's an arc much above the horizon versus all the lines here in North America.
Well, the reason that you're going to see, if I understand correct me if I misunderstood you, but I mean, this is 20 meters. So 20 meters were, about noon. So 20 meters is open right now. So there are lots of transmit and receive sites in North America and in Europe. So you'll see that's where there's a lot of traffic, reports going. And this doesn't show the direction. This is transmitters can be at one end or the other end of these arcs. But this is just a guess at the great circle route for these. This is not this doesn't attempt to display the actual path of propagation. It's basically showing the great circle route between the transmitter and the receiver. But the density of those is an indication of how many reports are being, and we're looking at the last 15 minutes. So if we went to a different band, like we can switch and look at what's happened, let's go up in frequency. Let's go to the 15-meter band. Okay, you can see not many, you can see 15 meters is, so now why here's a really interesting phenomenon that's appeared. DP0 gets incredible. I mean, the signal strengths from DP0 to Europe can be unbelievably strong and unbelievably stable. I mean, it looks like, there's 10 millihertz of Doppler shift on this path. And the signal levels are 20 to 25 dB stronger than any equivalent path I've ever seen.
It's like this, you don't.
I guess, I don't know. I'm not a scientist, so I don't know. It appears there's a ducting phenomenon, transequatorial ducting phenomenon. But they were, even the Germans, Michael and the people down there, I think were not aware of how open 10 and 15 meters were until they started looking at their whisper reports. And so I think is it doing an auto refresh? No, it isn't. Okay. So there are phenomena that you can observe that are unexpected and are helpful if what you're interested in is DX, then this is useful. Could be useful to you even if you're not interested in it. Yes, Elmer.
So what about FST4W? Are we
Okay.
going to walk away from that now and just focus on whisper?
No, well, okay. There are different ways to modulate. These whisper transmissions, like 4W, like FT8 and so on. These are frequency modulated signals. The transmitter is transmitting constantly, constant power output, but just varying the frequency. And by varying the frequency is how they encode the information, the call signs and so on. So there are different ways to modulate, to change the frequency. And we know that we've had this phenomenon with our cell phones. We had, first generation cell phones were analog, but when they got to the third generation, it was digital. But then there's a fourth generation. What did they change in the fourth generation? Well, one of the things they changed is they changed the way they modulated. They're still transmitting constant powers, and they're still modulating the frequency in our phones, but they're doing it in different ways. And the techniques used there are the basis of hundreds of years of mathematics, really. Fourier transforms, of course, underline the whole of these digital signal communications. But there's all kinds of in mathematics that have been we were using Viterbi encoding to now we have low density parity encoding that is much more efficient. So there are different modes of in the whisper world, the WJTX, that the first signal modulation mode was called whisper. And but 4 or 5 years ago, Joe Taylor introduced another more modern mode called FST4. And that's what's used by FT4 and FT8, this different modulation mode. And there is a parity of sister mode using those same more advanced modulation techniques called FST4. And Frisk something Taylor, I don't know what it stands for. It's the inventors, including Joe Taylor, who put the name on this. It doesn't describe how it works. But this mode results in slightly better sensitivities. For the same transmit power, you can hear a signal that is farther down in the noise with using this new modulation technique. So that's what one of the things we typically use is we use the 4W mode as our transmitter receivers.
Well, I'd like to thank Rob once again, so let's give him a nice. And you will have a chance to talk to him more about this over lunch. But before we go to lunch, we have a segue announcement or advertisement. Where's that microphone? Could you please give that to Drew Descator over there? Drew is going to talk about the event that Binghamton Amateur Radio Club is hosting this Saturday, and I'll explain why that has something to do with lunch in a minute.
Well, I'm president of the Binghamton Amateur Radio Association, and up in Binghamton, there is a Marconi Tower. So back in 1923, Marconi wanted to test the capability of being to actually communicate to a moving vehicle, in this case, a locomotive. And so Copernic and his crew built two 95-foot towers that were installed up in Binghamton next to the Lackawanna train station. But then also at the other end, they built two towers down here in Scranton, and it's going to be about 100 feet above where we're going to eat. It's actually, it was actually built on top of the Radisson Hotel. The tower clearly is not there any longer. We're going to see if we can sweet talk our way to the roof and see if there's anything left of that. But actually, this weekend is every April weekend closest to Marconi's birthday, which in this case it will be is this Saturday, is International Marconi Day. And there'll be stations throughout the world that will set up ham stations with special call signs specifically to sort of celebrate Marconi and have people talk to these Marconi sites. So K2M will be active. We actually tomorrow we got the Binghamton Fire Department that will come down, put some paracord up on the tower, and we'll be Saturday morning, we'll put up a couple of end-fed half-wave antennas, and we will be activating from there. So if you feel like a road trip is in your future, come on up tomorrow between 9 and 4, 9 a.m. and 4 p.m. We'll have stations there. We can get you on the air as well. But I'm really excited when I heard about where we're going to eat. I looked at the picture like I've seen that picture before. And sure enough, for those that are interested, I actually have a picture of a newspaper article that shows the tower on top of the Radisson Hotel. So, anyway.
Thank you so much, Drew. So yes, now we're going to go adjourn to lunch over at one of the historic Marconi radio sites. And so to do that, just at the end of this, if you are walking over, it's about a 0.25 mile, 0.4 mile walk from here. You can just find me and I will lead the group over. If you are driving over, you can